Hello, everyone. I hope you're doing well. It's Micah here, CS61B Tutor, and today I'll be teaching one of my favorite topics on sorting. Sorting is one of my favorite topics because of its usefulness in real-world applications. I mean, sorting is everywhere, and we oftentimes don't think about it. For example, Instagram. Instagram, quote unquote, sorts the feed rendered to you so that the posts that you might find to be the most interesting will show up first. So I'm going to assume you're all students in 61B and you've just watched sorting lecture on 2 times speed. And you kind of know what's going on, but the topic isn't sticking to you yet. But that's what this video is for. Like all my sections, I like to begin with my motivating problem. So the motivating problem is sorting a list of elements from least to greatest. Simple enough, but it easily scales to real-world applications. So let's say that I'm starting a car company. I have a list of car IDs that map to car instances. You might be wondering, okay, why do I have a 4A and a 4B? What's that all about? So I suppose that 4A and 4B are duplicate elements. So like two instances of like the Nissan Altima Super G6, whatever. They're just the same element. So how do I sort this? Well, there are a few algorithms to choose from, and that's why this topic is very interesting. Which algorithm is most efficient for our input? So first, we'll determine this empirically with the example above, but in the future, we want to, given an input, quickly determine the most efficient algorithm to use. Okay, before we get started, I'm going to go over some basic terminology really quick. Okay, so I get lots of questions about this. Best case. When I say that this sorting algorithm runs in theta n time, in the best case, that's the equivalent of saying that this sorting algorithm runs in omega n time, okay? In the worst case, when I say an algorithm runs in the worst case asymptotically theta n squared time, for an example, okay? That's the same thing as saying my program runs in big O of n squared time. A sorting algorithm is said to be stable if two objects with equal keys appear in the same order in the sorted output as they appear in the unsorted input. Okay, so a really quick example of this is, let's say I have 4, 2A, 2B, and then 6, 1, or something like that. After my sorting algorithm, it better be the case that 2A and 2B are in the same relative order as they were in our input. So this is the unsorted input, and this should be our sorted output. Notice that the 2A and the 2B are in the same order that it was presented in the unsorted case. Now let's move on to an example. Let's begin with our first sorting algorithm, insertion sort. This is going to be the most basic sort you'll learn next to selection sort. Sorting 8 elements, that sounds like a pretty big problem. But sorting 1 element is easy. Sorting 2 elements is also easy. Sorting 3 elements, given that the first 2 elements are sorted, is also not too hard. The main idea is that we have a growing sorted portion and decreasing unsorted portion, and we bubble elements down into its sorted place by swapping. Let's walk through an example together. Like I said before, we have a growing sorted portion, and that starts on the left side, and a decreasing unsorted portion, and that's this right side. So our sorted portion is already sorted because it only consists of 1 element. So we can move on. We move that blue bar by 1 so that now our sorted portion is 2 and 1. But this isn't sorted. So we ask ourselves the question when we do this process of moving the blue bar, we ask ourselves, is 1 less than 2? The answer is yes. So we swap 1 with 2. We bubble it down. Now we can move on. We move that blue bar to the right by 1, and then we ask ourselves the same question. Is 8 less than 2? We see that the answer is no, it is not. So we leave 8 in its place and we ask ourselves, are we done? Well, yes, we are done. The reason for that is that we know that the first two elements are already in sorted order. So adding that third element and saying that the third element is not less than the last element of this sorted portion means that we are done because this sorted portion is already sorted. We continue the same process for 4a, 6, 7, 9, and 4. You'll see that the 4a, just a quick bit of analysis, this 4a will come in between the 2 and the 8. It will have one swap, or one inversion, as we like to call it. And then this 6 will go here, and so on and so forth. I wanted to skip to the second to last step to demonstrate something about insertion sort's stability. So we run the same question of asking ourselves, is 4 less than 9? It is, so we swap it. Then we swap 4b with 8. It is less than 8. Then we ask ourselves, is 4b less than 7? Yes, it is. Is 4b less than 6? Yes, it is. But is 4b less than 4a? Strictly less than 4a? We see that it is not. So we insert 4b here, such that our resulting array is as follows: 1, 2, 4a, 4b, 6, 7, 8, and 9. So when we're talking about the topic of stability, insertion sort is stable. See that insertion sort is stable for all cases since we're always bubbling down from right to left and checking if elements are strictly less than the previous element. So when we ask that if 4b is less than 4a, the answer is no, so they will remain in the relative order that they were in originally. To conclude insertion sort, let's talk about runtime analysis. How does the number of inversions or swaps grow as n approaches infinity? In the best case, you'll notice that in our example, that there are no additional inversions when an element is already in the correct place, that is in sorted order. So the example I'm referring to is here. This 8 was already in sorted place. We asked ourselves, is 8 less than 2? No, so we're done with that step. So what if that was true for all steps? Well, this is the same as saying, well, what if our array was already sorted? Our input array is sorted already or nearly sorted. Then we're just iterating through the array and asking the question if the current element is less than 1 before it. But the answer is no for all n elements, thus we only make n checks. So a sorted list is then our best case scenario. But what's the worst case scenario? Well, the worst case scenario is when we have the maximum amount of switches, swaps, or inversions for each of the steps. It might help if we walk through a small example. Say we have the list 5, 4, 3, 2, 1. Our sorted portion right now is 5 and 4, but we have to bubble down 4. So we have to swap once. We run the process again. We see that 3 is less than 5, so we swap there. And then we also see that 3 is less than 4, so we swap there. So there are 2 swaps. Okay, we run the process once again. Is 2 less than 5? Yes, it is. Is 2 less than 4? Yes, it is. Is 2 less than 3? Yes, it is. So we swap 3 times. So we make 3 inversions. And so hopefully by now you can see a pattern that we're actually running into a summation that is famous. So we had 1 inversion plus 2 inversions plus 3 inversions at the third step, plus 4 inversions at the fifth step, fourth step, and then this continues on for all elements, for all n elements. And recognize that this is a famous summation, strictly the sum for I equals 1 from I to n. And asymptotically, we know that this is equal to theta of n squared. The next sort that we'll go over is selection sort. So again, we have a growing sorted portion and decreasing sorted portion. But this time we find smallest we select the next lowest element. So we find smallest and we quote unquote append to our sorted portion until we've gone through all elements. So I say append, but I really mean swap into the right place, since this sort takes place within the array. So let's walk through an example. The first step, once again, is to select the lowest element in the unsorted portion of our array. In this case, the smallest element is 1. And then we swap the 1 and the 2. Then we run the same process for the unsorted portion of our array, and we'll find that 2 is the smallest element. We run the same process again on the unsorted portion of the array, and we ask ourselves, recall that this is the unsorted portion, and we ask ourselves, what is the smallest element that can go in this place? We see that the answer to that is here, 4A. Okay, notice something here, and where I'm going to comment on stability again. We ask ourselves, is selection sort stable? The answer is yes, but it depends on how find_min is implemented. Find_min should iterate through the unsorted portion, keeping track of the minimum element and always asking, is this element strictly less than my existing best element? So on this unsorted portion of the array, 4A will be my existing best element. So then when I get to 4B and I ask myself, is 4B strictly less than the existing best element 4A? We see that it is not. So 4A is the one that we choose to be swapped into place before 4B, therefore maintaining the relative order in the sorted output as in the sorted input. So we continue this process for all the rest of the elements, and we'll get the same answer as we got in part A. Now let's talk about runtime. How long does each step take, and how many steps are there? So we see that each step runs proportionally to the length of the unsorted array. So for this example, at the start, the length of the unsorted array is size n, or 8 in this case. And then after swapping the minimum into its place into the sorted portion, the unsorted portion is length n-1. And then we get n-2, and so on and so forth until the end of the array. So how can I represent that as a summation? Well, this is the same thing as n plus n-1 plus n-2. And I said that we repeat this process for all n elements. So we see that this is actually a famous summation. It is the summation from I equals 1 to n adding all I. Asymptotically, this is the same thing as theta n squared. Next, we'll go over merge sort. Merge sort is a very powerful and asymptotically impressive algorithm. It's a divide and conquer approach to sorting. And oftentimes we'll use a tree diagram to help us visualize what's going on. So we begin with our example that we started with the car IDs. How would I do step 1, which is split in half recursively? Well, pretty much what we'll do is imagine that we're drawing a divider that halves the array, and then we recursively call merge sort on the respective halves. And we repeat that process of drawing that middle line in the center of the unsorted portions until we get these individual elements or individual nodes. Step 2 is to merge recursively. We recursively merge the elements together while comparing elements to fetch the right order. So what does that mean? Well, here we compare elements 1 and 2 in order to get 1, 2. So imagine, these are all single nodes, and we do this process of comparing elements to form this double node. Same process here. We compare, we see that 4A is less than 8. So we swap like that, and we form this double node. We form double nodes, and each of these elements are in sorted order. Each of these nodes are in sorted order. Then we run the same process. Let's combine these two double nodes into a 4 node. We're going to look at 1 and 4A, and we're going to see, okay, which one goes first. In this case, we have the 1 go first. Then we compare 2 and 4a, which goes first. We see once again that 2 goes first. And since there's no more elements in this array, we can just pretty much append the rest of this array to this 4 node. So we have 4a and 8, and this makes our sorted 4 node. The same process goes on here. We compare that 6 and that 4b. We see that the 4b comes down first. Then we compare the 9 and the 6. We see that the 6 comes down first. And then we compare the 7 and the 9. We see that the 7 goes first. And then lastly, we put the 9. And this is our sorted 4 node for the right side. The same process occurs, and we get 1, 2, and then now let's pause. It turns out that merge sort is stable. So during merge sort, to break ties, we always choose the left side. That is, if we were comparing 4a and 4b like we are here, we ask ourselves, is 4a less than or equal to 4b? Since it is, 4a will be placed down first and will always be placed down first. So we put down 4a, then 4b. So this implies that, yes, merge sort is stable. Now let's do some runtime analysis. What's the height of our tree and what's the work per level? So I love merge sort because of the beautiful tree structure, balanced tree structure that it employs. So we know that the height of this tree is going to be log n because we're just splitting by a factor of 2 at each level. Similarly, the height of this mirroring tree is also log n. So the total height is 2 log n. How much work is done per level? N. Total input per level is equal to n still. That is, total work is equal to the work per level times number of levels. Since the work per level is constantly n. So plugging in numbers is n times the number of levels times 2 log n. This is equal to 2n log n. We drop constants, so asymptotically, this is n log n. Now on to heap sort. Heap sort takes advantage of the fact that priority queues will always have either the minimum or maximum element at the start of the array or at the top of the heap. So I'm going to assume here that you have a fundamental understanding of heaps and how they're implemented. So if you don't know how to do things like heapify or remove max, I'm going to encourage you to watch week 11 question 1 for the tutorial worksheet videos if you're curious on how to do that. Let's walk through this example together. You'll notice here that this is not the original input array. Like I said, step 1 is to heapify the array. So what you see here is the heapified version of the array. We can see this, we notice this because the 9, the highest element, the maximum element in the array, is the first element in the array. Represented as a tree structure, it looks like this. Remove the 9. Okay, recall that 4 heaps, pick out the 9, and then we add the last element in the heap. Notice here, heap sort is unstable. Strictly, we'll see that in this example that 4b quickly jumped to a position such that it would be called first in the series of remove max calls. So what I encourage you all to do is to work this out yourself to be convinced of this. Really quickly, I'd like to recall the heap invariant for a max priority queue. The heap invariant here is that all nodes must be greater than or equal to their children. I'm going to ask myself, is 4b greater than or equal to its children? We see that that is not the case. So we're going to swap 4b with the greater of the 2 children, which is 8. Then I ask myself, is 4b greater than the 2 children, 7 and 2? We see that it is not. 7 is greater than 4b, so we swap those 2 elements. Now, we can read this as an array And so in the next step, our heap will look, or our array will look like, and our sorted portion here contains the max that we removed, 9. So what's the runtime? How long does it take to heapify? How long does it take to remove max? And how many times is remove max called? If all elements are unique and they're in no particular order, the amount of time that it takes to heapify in the worst case is n log n. And we saw this in the last week's worksheet, that this would take n log n to heapify. How long does it take to remove max? Well, to remove max, it would take data log n time. How many times is it called? It will be called n times for each of the elements in the array. Okay, so asymptotically, if we combine these together, this is going to be, so this is going to be equal to 2n log n. We drop constants again. So asymptotically, the worst case runtime is n log n. Okay, so what about in the best case? Well, the best case is if all elements are the same. Like what if we had 4, 4, 4, 4? So then our heap would look something like this. So then if we think about it, heapification would take n time because the array is already in heap form. That is, all elements are greater than or equal to their children. Now, how long does it take to remove max? Well, it's constant time because if we were to remove the element of the array, this quote-unquote unsorted portion is already in proper heap form. That is, to represent these 3 4s, it looks like 4, 4, 4, and so the heap invariant remains true. How many times do we do this? We apply this n times. So if we work through the summation again, this is the same thing as n plus n, which is equal to 2n, drop constants. Asymptotically, the best case runtime is theta of n. Lastly, we'll cover quicksort. Like merge sort, quicksort is also a divide and conquer approach to sorting. So let's take a look at this example. So step 1, we select our pivot. We have 9, 6, 8, 4a, 1, 7, 2b. So there are numerous ways to select pivots, and this is a heavily debated topic in the computer science world. There are some pivots that are better than others, but for now, we'll select a random pivot, let's say 6, okay? We'll see that randomly selecting a pivot is actually the empirically best approach. The second step is to divide our array into 3 groups: elements that are less than 6, elements that are equal to 6, and elements that are greater than 6. For the first category, we can see the elements that are less than 6 are 4a, 1, 2, 4b. Equal to 6, just 6. Greater than 6, 9, 8, 7. In practice, this is done through a method called Tony-Hoare partitioning, which I won't cover here because it would take quite a bit of time. But I encourage you all to search it up on YouTube, and the first result is by a channel called Computer Science, and they can explain it way better than I can, and probably better than most professors and TAs can. So I encourage you to do that. Step 3 is to recursively call quicksort on the greater than and less than subgroups. Here, you'll see to begin why we end up with a tree-like structure. So our array looks like this, and we call quicksort again on these 2 subgroups, okay? So basically, we'll pretty much run through the same process of selecting a pivot. I might select the pivot randomly to be 2, and then here I might select a random pivot to be like 8, and we'll run the same process over and over until eventually we have a sorted array. It's hard to show it rigorously here, but we will find out eventually that quicksort is stable. If we're using the Tony-Hoare partitioning scheme, and only swapping when an element is strictly greater than the pivot. And I encourage you again to see the Tony Hoare partitioning examples for more proof. Now a bit of runtime analysis. Again, like merge sort, what's the height of our tree and what's the work per level? In the best case, our tree is balanced. That is, the pivot is such that there's a relatively equal amount of elements here. So let's say there were 8 elements here. There's going to be about 4 elements here and 3 elements here. And then we continue on so that our trees are relatively bushy. That is to say that the pivot that we choose roughly the median of our sorted array. So then the height of our tree will be log n, and the work per level is n, but the total work we'll see that it is n log n in the best case. In the worst case, of course, is when the tree is spindly. So if we have around 8 elements here, then 7 elements here, then 6, and so on, that means the height of our tree is n, and the work is still going to be n plus, and then n minus 1, and then n minus 2, so on and so forth. So if we use that same sum, we get 1 plus 2 plus 1 plus n, which we recall is going to asymptotically be equal to theta of n squared. Here, the pivot is chosen in the order of the sorted array. Now, here is a table that summarizes all that we discussed today for the sorts that we went through. In practice, quicksort is normally the fastest. However, when input is small and relatively sorted, insertion sort works pretty well. And this is pretty much the case for my car company. I might use insertion sort because I have such a small input and part of the elements are already sorted.